So I wanted to give you an overview about what to expect in this chapter. This is sometimes considered pretty difficult material. Our book calls it chemical energy. Most textbooks would call it thermodynamics, maybe thermochemistry, something like that. But I like this because it helps you focus on what we really care about, and that's the application of thermodynamics to chemistry. We're really going to consider chemical energy. And I think that's key, that you understand we are going to focus specifically on chemistry. That'll help. What you need to understand is that why, and this is really why it's complex, I think, for many people, is that thermodynamics rules everything. Anything in this universe is controlled by thermodynamics in one way or another. Heat flow, entropy change, these are the matters that thermodynamics dwell on, so science, engineering, manufacturing, climate, communities even, like, how large can they be, which population dynamics. I've just picked some basic ideas, but it would be difficult to talk about anything technical that thermodynamics didn't play a role. But really, in all of these cases, it comes down to the basic fact that energy is conserved and entropy doesn't increase. But because there are application to so many areas, there's lots of different symbols used, and it's talked about in different ways. And that adds, there's sign conventions and all these kind of difficulties that we could encounter. But here's what I want to, and that's why I wanted to lay down this basic video that you could pull up and remind yourself all the time. We are going to focus on chemistry. And so the things that I'm going to talk about, the things that are in your book, the problems that we are going to deal with, they're chemistry problems. And you may, even if you're going to if you're going to engineering, the sign conventions are different. For example, we're really going to talk about two energy quantities, internal energy and enthalpy. Even this thing called internal energy, which I'll show you what that is. You know what it is when it comes to chemistry already. But we give it this name, internal energy. It's given the symbol E, capital E. So we're looking at changes in E, delta E, in chemistry. You may see it other places as U, the internal energy. Probably formally that's the proper symbol for it. That's most widely used as U, but we use E because it is energy, and it's the internal energy in chemical systems. And enthalpy is a part of that, and I'll show you exactly how that works in chemistry. So this is important that you get this, that there's ways to make this more complicated, and that's the other thing that happens, is that since it can be applied in so many areas, these specific applications are made abstract, and so quite often there are equations that are expressed, or as I said, language changes. It's about making general these applications. We're going to try and keep things real concrete. And so, although we'll use equations, I hope you'll know exactly what they apply to and when to use them. That's what we're hoping to do. That's what I'll show you in the next few minutes that I want to talk about here today, and that's what we'll deal with in class. Okay, so this is just a reiteration of what I said, that this is the bigger challenge, that this specific way to apply thoughts and ways to deal with changes of energy and entropy in chemistry systems, the specific is made more general, and it applies to everything. We're always going to be thinking about chemical reactions, always. Keep that in mind. We're going to make this kind of theoretical, abstract topic practical. That's my focus. So we'll start with this simple definition of, it's going to be about energy, and simply put, energy can be two forms. It's either potential energy or kinetic energy. That's it. That's this internal energy. And then I'll show you what that means in chemical systems, but just generally, potential energy. I put this little picture of the ball on top of the table. Okay, the ball wants to be on the ground. I've used this example in class. You want to lay on a couch, or at least I do, maybe you don't. We want to be at our lowest energy. We have potential when we're not at that. Potentially, we can go to a lower energy state. Things can change. That ball can move to the floor, but right now, because it's at a height, it's containing potential energy. PE, potential energy. But now let's say that ball rolls off the table and I hook up a contraption to where I put a rope to that ball, and that ball is around a pulley, and then I have a little tiny dog that I want to pull up on top of the table. The ball falls to the ground, pulling that string, and the dog, boop, all of a sudden is up on the table. It does some work. We have to turn that potential energy into kinetic energy. The kinetic energy is how the system does some work. We're going to talk about that system surrounding things, but it's not hard in chemistry because, well, we'll get to that. But there's two forms of energy, potential and kinetic. In chemistry, potential energy is stored in molecules, and we do a chemical reaction which liberates that potential energy or changes it, and that allows some work or heat or something to be created. And that's what we'll look at right now. So when we talk about energy in chemistry, right, we're going to really, chemical reaction, and I always go back to my same thing, A plus B goes to make C. Energy is consumed or energy is created. This is this potential energy becoming kinetic energy. A potential becomes a usable form of energy. And where does that come from? Well, this is why we've done everything in Chem 101. So let's go back and think about, what do we learn about hydrogen atoms? And it's a chemical system. It's the simplest one, and that's all I'm talking about. Not that it's the most interesting, but remember hydrogen. Hydrogen has one electron in it, right? I'll just draw one electron in it. That one electron is in a 1s orbital. And remember, s orbitals want to have two electrons in them, so it is not filled. That is an unstable state. It can lower the energy of that hydrogen by putting one more electron in it. Now, how does that happen? Well, remember we draw these images. It's an s orbital. Well, hydrogen is always moving around, and it's bumping in or colliding with many other things, and one of those things that might collide with is another hydrogen. And remember, they will form a covalent bond. They will share two electrons. It's the overlap of one s orbital on one hydrogen with the s orbital on the other, and that makes H2. So in this particular system, we're going to have H. So I've drawn the scale energy along the X. So it doesn't matter what the numbers are here. We've got energy in joules on that left, and the energy of two of these hydrogens is at, we'll call that arbitrarily our 0 joules. If that's a high energy state, because it has one unpaired electron and it needs two electrons to fill that shell, when they collide with each other, they share that electron, and we think of each hydrogen having now a filled shell. And that stabilizes. So down here is going to be that H2 molecule. That's actually this one. There's a lowering of energy. And that is storage of energy. That's the potential energy. There is energy stored in this chemical bond that can come out. But in terms of thinking about energy, it is important for you to understand H2 is the stable molecule, and if we're going to break that bond, we're going to have to put energy into it, But when the bond is formed, it lowers the energy, but it doesn't lower the energy in a kinetic sense. That lowering of energy is because it's taking energy and putting it into potential energy. And that's what's happening in chemical reactions. We are breaking chemical bonds. We are making chemical bonds. It costs energy, right? It goes uphill to break the chemical bonds, but we get energy back out when we make chemical bonds. So if we make more stable chemical bonds, then are broken, we're going to store energy. But if we have extra energy at the end, energy is going to be usable. And that's how it goes back and forth between potential and kinetic energy. That's what's happening in chemical systems. We are breaking and making chemical bonds and chemical reactions, and that's how we're tapping into potential energy. But that potential energy is the chemical bond, and it turns into kinetic energy when they are rearranged or broken and reformed, and there is leftover energy, and that extra energy has to go into movement of those atoms. That movement of atoms can either heat things up or be used to do work. And that's going to be our first definition, this internal energy, E. So let me just even write this down. E is going to be defined as being two parts: a heat and the work it can do. That's what the energy in a chemical system is. It is the internal energy of a chemical system, and it's defined to be Q plus W. So that's going to be our first definition of one of the things you're going to have to calculate. Total energy, internal energy, E. And most of the time, we are going to want to calculate what we call the delta energy, the change in the energy. So never forget this delta symbol. That's always going to be defined as whatever our final process is. So chemical reaction, that would be the products minus the reactants, right? Or the initial. So products minus reactants, that would be a delta internal energy, E. Or it could be, final minus initial. That's always what it is. Okay, so E is the heat, we call Q, and the work it does. And we're going to get specific eventually those. But that's going to be one thing you're going to have to be able to calculate, and I'll show you ways to do that. And the other one is, and you're probably more familiar with this, you've seen this thing called enthalpy before. And that's really just Q. That's just the heat. And the reason why this is what we're more interested in chemistry is because it's really internal energy change, this changing, breaking, and making chemical bonds that occurs. But it's done under conditions of, we usually even do this, we say constant pressure. So if you have a beaker out on the bench and you're mixing A out of one beaker and B out of another beaker, so this up here, A plus B makes C, and it's going to create some amount of heat, that's the enthalpy change, because if it's out in the open on the table, it's always at 1 atmosphere or whatever pressure you're at, right? It's under conditions where pressure doesn't change. It's at constant pressure, and that gets rid of the work. And I'll show you about that in a minute. But I just am here trying to introduce you to these two ideas. Now I hope you have an idea what internal energy is. It's, this storage of energy in chemical bonds, and when a chemical reaction or some process occurs, it typically creates heat and does some work. And when it's out on the bench, it's done under constant pressure conditions, and that's the enthalpy. And that's why you have probably learned about enthalpy and not so much about internal energy. Internal energy is becoming much more important because there are now ways to make chemical systems do work that don't involve converting things into hotter materials and using that heat in some way. Up until this point, we burn things. That's what our economy is based on, combustion. The internal combustion engine, and that's how we get most of our energy. But that's changing, right? We are starting to see work being done by solar cells, or maybe by windmills, or there are other ways. We have never had to really concentrate too much on how we need to extract energy out of out of what's around us because we had more than enough fuel, and that's changing. So that's why thermodynamics is important, and you're going to apply these in a lot of different areas. But in chemistry, we're really dealing with these two ideas: internal energy. That's the total, and that'll be a more general approach. But we focus on the enthalpy, delta H, or H, because it's really just the heat that turns into kinetic energy, and we use that kinetic energy in some process. So we're going to take those ideas and go forward with them, and that's what we'll be doing in the rest of this chapter. I want to focus on a couple more ideas, and then we're done with this. And these are things that, again, cause confusion because, as I said, thermodynamics can be applied to so many different areas and so many different things. And one of the tricky parts of it always is defining what's called the system and the surroundings. It's not hard in chemistry. And even if you read in our book, if you read in any book, they're talking about system versus surroundings. But because in chemistry we're doing chemical reactions or some process that involves molecules or atoms. And I've written down here, generic A plus B will produce a product C. And, so in my image here, the yellow picture pouring into the beaker is A and the blue one's B, and it makes products as they combine, and we'll call that C. And then I've drawn this more schematically on the right, my beautiful art. Remember, we've got molecules of A and molecules of B, or atoms, and they are colliding with each other, and they form product C. That we will define as the system. So keep that in mind when it gets complicated, or somebody starts talking about system versus surroundings. Our chemistry, our molecules, our chemical reaction, even if we're just heating up and boiling water, liquid, arrow, water, gas. That's the system. And then the surroundings, like in this case, A plus B, it's done in water. That's why I've made it in an aqueous solution. The system are A and B and C. That's a chemical reaction, and it's going to produce some amount of heat because of those bonds breaking and forming. And it's going to pass that heat or do the work on surroundings. And in our case, surroundings are typically the solution, the water. So system, chemicals, A and B, surroundings, and C, and surroundings are what it's done in. And I'll be careful to try and, again, make that point as we do problems, but that's really it. Now, you apply it to different systems and it can become more complex. Not chemistry. Chemistry, system is A plus B giving C, the chemical reaction. Surroundings are what it's done in, like water. And it collects, the temperature rises because A plus B to make C creates heat. That heat goes into the surrounding, which is the water, and the temperature of the water rises. That's it. Now, the other thing that's going to be helpful to us is defining the properties of a state function. So I'm going to give you the answer here. The state functions that we're going to worry about are E, internal energy, and H, enthalpy. But here's why this is important. A state function, so that's a mathematical expression. It's a special kind of quantity. It doesn't matter how we calculate it. So here's the example. I have a mountain that I want to climb, and I have two paths, right? So that's what I'm trying to show here. Path A, I can zigzag up that trail. Take me 12 miles to get there, but the grade's much easier. It may take me longer. I still start at the bottom and I end at the top. That's the path I choose. That's path A. The other way to do this is go straight up the steep part. Path B, it's shorter, it's steeper. The change in the energy is the same, right? Or the elevation, I go from 0 to the top. It doesn't matter which path I take, I'm still going 10,000 feet. That's an example of a state function. It doesn't matter how we calculate it. So internal energy, E is a state function. Enthalpy is a state function, and we're always going to choose the easiest method to calculate it. Now that'll come in handy towards the, on Friday and Monday, but just know enthalpy, internal energy, both are state functions, and we're going to calculate them the easiest way possible. And that's it. See you in class.